We already discussed why sometimes we need to apply implicit differentiation. In this video, I'm going to show an example, and I'm working through an exam problem. They're giving us a curve, and they're asking us to find the equation of the tangent to the curve at the point where x is equal to 1 and y is positive. Okay, you're not going to do this in the exam, but just to help you understand what's going on, I'm going to show you a GeoGebra picture of how the curve looks like. According to GeoGebra, this is our curve. It's only defined for x greater than 0 since we are applying the logarithm to the variable x. And as you can see, for the value x equals 1 that the question talks about, we have two options. It looks like there's a positive value that looks to be around 1/2, and there is also a negative value that looks to be around negative 1/2. In this question, they are asking us about the tangent at the point that has x coordinate 1 and the positive y coordinate. So you can look at the picture and more or less imagine how this tangent is going to be. We can see that it's going to have negative slope. So let's go ahead and apply the method of implicit differentiation. We have that 8y times logarithm of x minus 2x squared plus 4y squared has to be equal to 7. So if we take derivative on both sides with respect to x, we still have an equality here. On this side, derivative of 7 is 0, so that's easy. On the other side, we have three terms, so we're going to be taking the derivative of each of them. So the derivative of 8y logarithm of x with respect to x minus the derivative of 2x squared with respect to x plus the derivative of 4y squared with respect to x. All of this has to be equal to 0. The first term, we have to take the derivative. We have an 8 that we can take out from the derivative, and then we have to apply the product rule. We need to take the derivative of y with respect to x times logarithm of x. I'll use brackets here, plus, and then we're going to have y times the derivative of logarithm of x. Let me correct here. Logarithm of x with respect to x, and that's going to be our first term. For the second one, we have negative 2, and then we have the derivative of x squared with respect to x. That's just 2x. No mystery over there. And then for the next one, I'll take the 4 as a factor outside, and we need to do the derivative of y squared with respect to x. And when we get to this point, we have to be careful because actually here we need to apply the chain rule. Here we first have the variable x, we apply the function y, and then to that function we square it. So y of x squared. On the first step, we will be doing the derivative of y with respect to x. On the second step, we have 2 times our function. So putting this together, let me write first the two last terms since we have already worked those out. We have here negative 4x plus 8 dy dx times y, and all of this is equal to 0. So let's focus now on the bracket with the product rule we have over here. We have dy dx times logarithm of x plus y times, and now we need to take the derivative of the logarithm of x with respect to x, and that's 1 over x. So we're done taking derivatives. We may want to write this a little bit nicer. This is equal to 0, so we can divide everything by 4 to simplify the values a little bit over here. So we'll get that 2 dy dx times logarithm of x plus 2y over x minus x plus 2y dy dx is equal to 0. So what are we trying to find? We are trying to find an expression for dy dx. We have it over here. So we want to isolate for that derivative. So I'll write that 2 dy dx. I'm taking that as common factor between the first and the last term. We're going to have to multiply it by logarithm of x plus y. And then we can write on the other side the other term as x minus 2y over x. So final step, dy dx, if we isolate, is x minus 2y over x over 2 times logarithm of x plus y. Can I write this nicer? Yes, definitely. But remember that we're going to be caring about the case when x is equal to 1. So there are going to be many things in this expression that simplify. We also need y to be greater than 0, but we need to know what is y, because the expression we got over here for the derivative of y with respect to x is an expression that depends on x and on y. So for each value of x and y, we're going to get a result. So we need to find actually what is this y greater than 0 we are talking about. So we're going back to the original equation of the curve, and we are going to apply the fact that x is equal to 1. So that means that 8y times the logarithm of 1 minus 2 times y 1 squared plus 4y squared has to be equal to 7. This term is 0 because we have the logarithm of 1, which is 0. So we are having that y squared is equal to 7 plus 2 divided by 4. So y squared is 9 over 4. And we have the condition that we want y to be greater than 0. So y has to be 3 over 2, which matches what we saw in the picture in GeoGebra. So the point we are talking about is the point 1, 3, half. So let's go and see what happens with dy dx when we evaluate this expression at 1, 3, half. This line I wrote over here, that's the notation for evaluated at this point. So what do we get here? We're going to get 1 minus 2 times 3 over 2 divided by 1, so I won't bother to write it, over 2 times logarithm of 1, that's 0, so plus y with this 3 half. So this is 1 minus 3 over 3, so this is minus 2/3, which somehow matches the idea we had from the picture. Now, what were we trying to find? We were trying to find the equation of the tangent at the point 1, 3 half. So now we have all the information we need to write the equation of the tangent. I'll write it in the point slope form. Y minus 3 half has to be minus 2/3, so the slope times x minus 1. And that was what we were trying to find.